Okay, so I think we can start today's lecture on. We are gonna continue the topic of computer vision. We're gonna speak about different types of computer vision models, like the architectures, basically, which are used in computer vision, and generally the things that are like backbones of robotics vision, so to speak. And I'm gonna just write read this thing. So theory is when you know everything but nothing works. Practice is when you don't know anything. Welcome. Theory is when you know everything but nothing works. Practice is when you don't know anything yet everything works. In programming, in like computer vision and on robotics, there can be a lot of words here. We combine theory and practice, nothing works, and we don't know why. So the thing is, we're gonna learn theory today. I would like to speak about code and stuff, but there's so much things that need to be covered that I cannot just make that in one lecture. So I'm gonna try to make something happen in the next meeting. I'm gonna talk about it a bit later. So yeah, and next thing, work on practice. Nobody gives a shit about theoretical knowledge. Actually, like the things that I'm gonna tell you is like basic knowledge that you need to understand at least how something is working, how computer vision see. You are not gonna implement all of this thing from the start. We are just gonna, there are already state-of-the-art models that use, for example, CNNs or ViTs we're gonna talk today about. And if you really want to design new things, this is like the base thing you want to understand here. But actually you're not gonna implement all of this every time, but it's crucial to understand some basic knowledge about some computer vision models. So yeah, that's what we're gonna start from theory, then on practice. I'm gonna show you actually one practical usage of some CNN called YOLO. Maybe some of you heard something like this. Okay. Okay, convolutional neural networks. Those are basically the oldest good approach to do computer vision. The best, kind of old right now, because there's new one called ViT. We're gonna speak on it later, and they appeared in 1989. But in 2012, as I spoke last time, they become more popular. So yeah, they are popularized, and there were more development on them. Okay, so we're gonna just do a small recap from the last lecture, and just so we are on the same page, speaking about knowledge. So images. Okay, this is general thing we're gonna learn today about convolutional neural networks. So, okay, images are just numbers. I think this is the exactly good representation. I think everyone understands that we have like scale from 0 to 255, and there's like 0 is black, 255 is white, and on that scale we have some gray colors. I think it's basic knowledge. Yeah, colors images are 3-layer matrices. This is the example. Yeah, like have original picture, and it can be represented with 3 matrices. Just basically the combination of numbers, like. Someone is calling. Okay, whatever. Yeah. So like combining red, green, blue layers, we are getting color image. Yeah. So yeah, this is the basic things, and convolution. It's actually a new thing, new word, but we spoke on them last time. So okay, what is this thing? oh yeah, this is the representation of the convolution. So when we just apply kernels that we spoke last time, filters on some image, we're just doing convolution. So we are convolving through each pixel, through each, with our kernels, through every region, like 3x3 kernel, I don't know, like 4x4, whatever. And we are just changing the image somehow to get some features. More on that in a second. So yeah, this is just an example of a kernel. Like, yeah, like we do some, we have some matrix, and we just multiply by each number, and we get something like this. And like we do the dot product actually, and we get this kind of output. So yeah, this is just the basic knowledge we spoke last time. So okay, next thing is, okay, so the first layer of the convolutional neural network is we get the image. So you got this 3 layers of red, green, blue values, just 3 matrices, and you just convolve through with some kernel through that image, so you get the convolved image. And the thing is, we are convolving with very different kernels. So we get some, so by using the kernels, we just extract some features. I'm gonna show the hands-on example here. Okay, so let's take a look at how we can combine the kernels and how they can be done, how they can be implemented. So we got the input size, for example, the image. It can be like 10 by 10. Usually it's like larger, but for the sake of simplicity and the site shows like that, it's like 10 by 10. Like, what is the maximum? It's like 16, just whatever. We can change the kernel size as basically the largeness of the matrix we are convolving through the image. So, and the padding is actually a very interesting thing. So, because when our kernel goes, for example, here, it doesn't, in original image, it doesn't really know what to do. Like, you have 4x4 kernel, but you don't know like how do you like do the edge. So we add padding, so we can extract some features from that. It's actually not that important, so let's move on. Dilation, yeah, like just some interesting features. Like the more distinct those kernels are, the more features we can get from the image. That's really good visualizations I'm gonna show you. So there's also a thing called stride. Is actually very interesting. So as you can see here, we are just going through like each pixel one by one, 1, 2, 3, 4, 5, 6, 7, and so on. But if we do like, for example, 3, we make a step for 3 pixels and so on, and we just move on like that, and we create some output. The output differs on our kernel and our original image. So yeah, for example, this is how the future maps look like, and those are filters that were used on them. So as you can see, we extract some. Oh, okay. Okay. So we use that filter. We got this thing, and the thing is in convolutional neural networks that you need to get the more features that you can get from some number. For example, you can have so many different numbers. Like, for example, let's take this example, number 9. We can have very large amount of 9s written down, but generally they follow the same pattern. So when we convolve through them, we have like so much layers of convolution that, as you can see here, like we have 1 layer convolution, 2nd layer, and pooling. We're gonna speak to that. And so we are just taking the features. So for example, here we used one kernel, we will get the one new matrix. For example, in this example, there is like 3 different kernels went through that convolved through this image, so we got 3 different matrices, and on those convolved matrices, like new images, we convolve once again, so we get different matrices. There is good visualization actually.
So every time we use a different kernel, we get a new feature map.
Yep.
And every time like we do this pooling, we use kernels on the feature maps we've already gotten.
Pooling is kind of different from just applying kernels, because there's going to be a good visualization. I'm going to show you in 1 second, which will answer your question. So also there are strides, and I want to just read something that I have written down here. So a larger stride will produce smaller output dimensions, as it covers the input image faster, as I showed before, whereas the smaller strides result in a larger output dimensions. Increasing the stride will allow the filter to cover a larger area of the input image, which can be useful for capturing more global features. And yeah, like the first layers are just gathering some global thing, like when we convolve through in the future, like there are larger features, so to speak. Yeah, okay. Okay, so let's, this is the padding actually I described. So yeah, there's matrix, there's just zeros on the sides, and this is the okay, let's let's go through visualization so we don't get lost here. Okay. So for example, we got the red, green, blue channel. There are those just 3 matrices. For example, here we just use some kernel, as I described. Those are just 3 by 3 kernels with can I? Yeah. Okay. These are just 3 by 3 kernels that convolve through the image, and they make new output with the new size. And okay, let's stick on the size here. For example, second layer, we got, there was like 62, and we got 60 by 60 here. So all of that can be calculated in this kind of formula. So we just put the input size, the padding, the kernel size, and the stride. All of the features that we can have in the kernel, we just put here, and we get the output size of the new image. So yeah, and in this layer, we got, for example, this one. So kernel convolves through every pixel here, and it gets new output. So it's kind of this like extracting some features for us like here, and then they just sum up, and we get this new convolved picture. After that, we use the ReLU activation. Is just an activation function. I don't know, maybe like a lot of you from like study AI. So, but for those who don't, I'm gonna just write what is ReLU. So ReLU is just an activation function, which looks like that. So for example, here we have some some 0, -1, -2 and stuff. So up until the value of each pixel is less than 0, it's assigned 0. For example, as we can see here, this pixel is -41, so it's 0. So what do we write? Like everything that is less than 0 is 0. This is the value. This is the like new value. This is the old value. And after that, after it surpasses the 0, so for example here, it just assigns the value of the pixel that we got. So this is correct linearly. Is it clear?
Mm-hmm.
Okay. Just very simple thing, like if we get some.
Why are we using this function?
This is the part of the convolution, neural networks. When we got the convolved image, like as described here, we use the ReLU for some kind of new features extraction. Someone thought, oh, that would be cool that if we use ReLU, that we can extract some cool features. So let's use ReLU to get our model, like to get the better features, so to speak. So, for example, same here. If we get something more than 0, then it's assigned to 0. Then it's assigned to its value. But for example, if we go here, we see that here is like minus. Okay, you saw probably. Okay. When it's less than 0, the pixel value is just stays the same. I think it's simple. So the thing is about convolutional neural networks and their architecture is that like different convolutional neural network use different architectures. So for example, some of them can use 3x3 kernels or 7x, like the first one we're using, the one first that succeeded was using 11 by 11 kernel. So it was distracting very like general features. It was not going into details, like because when we use some small kernels, we just detect very small, very precise, some very precise details. So the big ones are good in some cases, but but yeah, this is at the sake of the understanding which features we get from which kernels. So yeah, this is important. Yeah. So yeah, for example, this is the ReLU activation thing. If you wonder how it generally looks, this is like, okay, let's do the first one. It takes the original image, it convolves through every RGB picture, and it just gives us some output. So, and yeah, these all layers are just for getting some features from a cup. So, for example, and as you can see here at the end, all of them are kind of blurry, right? So what do we want to expect from that? That if we take a different cup from, for example, different angle and put through all of this same kernels convolutions and like all of these changes, so we do the same changes on some different image of a cup, in the end we get something like this, like because it's so blurry, it extracts some features. For example, if we took the image from some other like angle, this thing would generally be the same. So yeah, and if you don't understand something, be be very like just ask, because I might also be confused with some things. Maybe I confuse some things when I describe something. So like, don't be afraid. Okay, next part is pooling. In pooling, we're not applying any kernel to the input data. We are just simplifying the information with the math operation. So in this thing, we are kind of decreasing our matrix. For example, the dimensions are decreasing like so much. For example, in the convolution, it was like the original image was 64 by 64, and now it's 62 by 62. So it's not that much, but to get the general features, we need to do max pooling. For example, what is max pooling is we take, for example, we have some kernel here, like it's 2 by 2, okay? So we got different, okay, it's Control C. Okay, we got different values in our kernel. So max pooling, there are kind of two different approaches with max pooling: the average pooling, with pooling, the max pooling, or the average pooling. So in max pooling, we just in our kernel we extract the maximum value of a pixel that is in some kernel. So we get this out, and it just assign. So it gets more like saturation. It gets like concentrated in the end, and we also decrease the amount of pixels, so it's simpler for our neural network to learn. Yeah.
Could we invent new types of pooling? For example, like minimum pooling or mean pooling?
Like theoretically, you can change like everything here, but I mean maybe no, they probably don't use those kind of things, but maybe if you would like to design your own convolutional neural network, there are some tools for that. I didn't cover them here, but there are some. If you learn them, you can do that. So maybe you can get different features from the some images, so you can train better. Because like,
so just to specialize the neural network in something.
Max pooling is to like.
I mean,
we need to.
The different types of pooling would be to specialize the neural network in like, seeing one thing over the other.
Yeah, and like there are like two types of max pooling actually, and I'm not sure what do you mean by specialized neural networks.
I mean, I'm just not sure how the type of pooling we use would like
Affect on the
affect the features we
this
get.
is the you can think logically here. For example, if we take, for example, in this convolution layer,
Yes.
I'm not sure if you all understand, but what we are doing here is the same thing as here. Is it clear? Like this, like this part. We're like the convolution is those kernels changed. So like for example, let's take a look here, and this is the same thing here. Like this is just second thing, the first thing, and the
Original image, yeah.
yeah, the original image. So it's I think it's straightforward. For example, if we would use here, okay, let me just do the better. Okay. For example, if we would use here not the max pooling, but the average pooling, we would just sum these things up and divide them by 4. So because the average pooling is that you take the average of the kernel,
Yes.
not the maximum value.
Yeah, just
So-
the average.
Yeah, so just the average would be like not 2 by, for example, 1.3. So it would be less blue, for example, here. So it will not extract as many features as we expect. And it's just the question of implementing things, because you need to understand what do you want to for your convolutional neural network to get in the end. So, and according on that, you need to decide what kind of max pooling or kernels you need to use, because like as I said, the first one were just kernels that we're extracting, and some max poolings basically make, I'm not sure which ones, but, and I'm not even sure that they were max poolings, but they were kind of large kernels, and if we get the large kernels, our convolutional neural network is kind of sucks, because the smaller the kernels, the more like detailed features we will get, like from some cup, like some corners. If we take the large kernel, we don't get the edge of a cup, we get the half of the cup, for example, and it's not that clear for neural network to learn in the end. And it's actually no neural network here yet. Just 1 second. And okay, so, and the neural networks happened somewhere. Okay, I'm not sure where it is on this image, but here it is on this image. So after we do the pooling, so okay, wait, did we do the pooling multiple times, or we just did one? Okay, we did 2 times here in this example. So last thing we get this kind of blurry, you might say, image of a cup, but it actually describes some features for our neural network. So after we get all of these kernels, the last our kind of matrices with values, we just flatten them. So what I mean by flatten, I'm not sure if there is visualization of that. Okay, there is, but it's so small. So for example, okay, I'm just gonna try to visualize it here. So, to be clear, for example, we have like okay, so what do I mean by flatten? That we have some like 13 by 13 the image, the dimension is 13 by 13 here, and we get that like 10 of them. So what do we want to do? We want to just take every pixel and just flatten them. For example, we have like, I'm not gonna write, I'm not gonna paint here like all of 10 matrices, but just the second one for the sake of example. Like, I don't know, like 13, 3, 4, 6, and like whatever. Okay, let's 5, 6, 7, 8. So what do I mean by flatten? So think of this as this is the matrix. Imagine that this is the same matrix here, or whatever. And what do I mean by flatten? We take some amount of matrices and just make them one array of numbers. For example, it gets 0, 1, 2, 3, 4, 9, oh no, 8, like, comma,
0 to 8.
0 to 8, and because we just flatten all these things, the next one is 13, 3, 4, and we go.
Just get the value of each pixel of each matrix, and
yeah,
get,
exactly.
Create an array of them.
Exactly. So we just create an array, and maybe someone knows why do we do that.
For the input of deep neural network.
Exactly. Because neural networks learn from, like, they they need some data to learn from, and some starting nodes, the first layer of the neural networks, and we just feed the pixels to the deep neural network, so it gets like through some amount of like, let's call this black box. It goes through black box, like the neural network operations. We don't know actually what's going on there in the deep learning networks. So at the end, get the output. I'm gonna just show you. I hope there's, yeah, like something like this. So this layer is our, like, for example, this can be 0, 1, 2, 3, 4, 5, and so on until we like done with our pixels from our matrices. Here is just what described. I'm not sure why it's described so poorly and we cannot see actually, but okay, whatever. Yeah, and then we get our output. Yeah, it goes through softmax function, but it's I'm not sure why. Okay, this is just a part of the deep learning neural network. So at the end, we just get the output from those pixels. And okay, so but the thing is, when we train the convolutional neural network, because we don't design, and I'm gonna answer your question again. You asked me before like about kernels and their structure. I forgot to tell that to you, but wait, I got it somewhere here. What do we train here? So the thing is, we train our neural network. We've predefined some layers with kernels, but we only describe the size of this kernel. Like for example, here is 5 by 5. There is real function. There is 3 by 3 kernel, and so on. And there is this neural network. Wait a second. Do you all know what is softmax? No. Maybe someone who wants to explain. I mean, I can explain, but maybe someone wants. So I'm gonna just, for example, we put our image through deep neural network, deep learning neural network, and at the end we have, like, for example, for a number we got 10 options. For example, 1, 2, 3, 4, 5, 6, 7, and how do we choose from this neural network which
probabilistic?
Yeah, it's kind of probabilistic thing. How do we choose which thing we like? Which number do we choose from that? Here comes the softmax function. So at the end of deep neural network, we got some probabilities here, right?
Yeah. So we have to turn this, let's say, activation, maybe value into probabilities of each possible output.
So for example, we get here for 0.1, for example, the original image was looking something like, I don't know, 2, okay? So for 1, there is, like, for example, 0.1 probability. For 2, there's, for example, 0.5. Okay, it might be bad deep neural network, and so on. For example, here it might be 0.3, 0. I don't know, 0.1, 0.202, 1. I don't know, whatever. And I mean, they not sum up to 1, but they should sum up to 1. So, yeah, and we just choose the most probable thing. Yeah, and that's how we choose the two. I think I confused something with softmax, because softmax is when you do the sum of the probabilities. You divide them by the amount of probabilities you added.
Yeah, so basically at the end you have the values of each, let's say, node, and then you have this exponential function. So the more active the node is, the more value from the entire thing it gets, and then you normalize it because you have to.
Yeah, the normalization, getting to the percentage, getting to the value that we extract our answer from is just the softmax function. I think you would understand it better if someone else explains to you, for example, on Google, because I may not be the best one to explain this. I'm pretty sure it was hard to explain. So yeah, in our convolutional neural network, we train this thing, our deep learning network, and we also train like these kernels, like their structure, for example, how they build, like should we choose one type of kernel or the other type of kernel in each layer. So yeah, that's how we train our model. That's how we train our convolutional neural network, and then we just choose which one is the better. We do some tests on them. But this is just another topic here. So we just choose some. I'm just gonna be real quick here. So we just, for example, we have like 100 images of numbers. We take 80 images of numbers, and we train our model, convolutional neural network model, on those images, and we get the result, and we compare those results to the other 20. There was the other 20 pictures. We know the answer, so we know how deep neural network is good. So yeah, and we choose the best one. Okay, ask some questions if you have them on convolutional neural network, because the next topic is visual transformers, and it was quite hard for me to learn. But so ask your questions now about convolutional neural networks if you have some doubts. So once again, the convolutional neural networks extract features, and they train the deep learning neural network on this array of extracted features. So these are just those matrices. Those matrices are just features, and we train on them our deep learning neural network. Yeah. Questions about convolutional neural network?
Could you switch the tab to convolution visualizer? I wanted to. So the kernel size gives us either the more global features or the more distinct ones.
If you get the smaller ones?
Yeah, they are more distinct. And how does stride impact the details of the features?
Okay, let's take a look at the example, for example. Stride. Here's the it visible? Okay, this is our output. This is our kernel. So when we change the stride, we kind of change the step, and the steps between those, like we sliding wheel, should we step like once or should we step like through 3 pixels to change something, to do the convolution through our image, right? So for example here, you're taking the convolution of it's too high, okay, of okay. You're taking convolution of this area. The convolution before that, it was this area, and we write down the answer in this pixel, the last one. Before that, it was this kernel. So we did the dot product. You know what is dot product? You multiply every pixel and add them. Yeah, we did that, and we get the next pixel. I mean, the previous was that. And so on. When we change the stride, for example, to 3. Okay, it's a bad example. Wait a second. Okay. So as you can see, the output is much smaller than it was before, and why it's smaller? Because we do a larger step. We change, for example, last time we went from here
we just went
to there, and now the stride is 3, so we are just moving. We are making larger step, but still we are assigning this value to the lower pixel, the next pixel.
Yeah.
So it extracts like more features, maybe, like from this kernel to 1 pixel. But I think with using large strides, we would lose some features.
Yeah, I guess the question was more like, does it lead to skipping parts of the image, or like,
no,
what are
we
the practical
cover
effects of using a higher or lower stride?
For example, if you use much higher stride, you actually will skip something.
So we would just skip this part of the image.
So we fit in our like dimensions. So for example, now I'm moving here. As you can see, the output is small, like 3 by 3 matrix.
Yeah.
And we are just skipping this. For example, this like I don't know, like thing. This
the row.
This area, yeah.
The column. Actually.
Yeah. Like we are using so much information, like losing so much information here. So the large strides are bad.
And the same thing goes with dilation, that we are just having these blank parts of kernel, kind of, and we are losing that.
Yeah, we are also, but maybe in some cases it might be useful. For example, if I don't know, if we want to detect some pattern, for example, of you have some I don't know rice, so like on the ground, and for example there is rice like over every big the whole image, and for example this if we choose the correct dilations, that would detect those like grains, rices, and they would just extract this in our matrix. But I'm not sure actually. It's just the sake of like you decide. You need to decide by yourself. But generally, the convolutional neural networks learns these values, because here is no values, as you can see at the kernel, and you just define the the dimensions of the kernel, and convolutional neural network trains, goes back and forth, checks if it was right, if it was not, about its prediction, and it tells you how to change this kernel. Is that clear?
Yes.
Cool. Yeah, it's actually cool that you ask questions. Yeah, I'm happy with that. Any other questions? Okay, I think no. So just some examples of convolutional neural networks. RCNN, fast CNN and faster RCNN. These are two-stage detectors. There's just different types of RCNN, CNN-based models. I'm not gonna dive into them because I'm not sure about all of them. For example, VGGNet. Is it? Okay, there's no information given about the. For example, okay. Take a look at this VGGNet, known as this is just a convolutional neural network, known for its simplicity and depth. The depth is the amount of convolution layers, so the amount of features we get, and it established the idea that stacking small kernels repeatedly is more effective than using larger kernels like 5 by 5 or 7 by 7. As I mentioned, like it's better to use small ones than the big ones. So yeah, this neural network just learn that. And YOLO. About YOLO, I'm gonna show something. Okay. This is project. Okay, well, actually I want to show this one. This is the convolutional neural network working on real robot, and yeah. Oh, for example, as you could see here, it detected my knee as an apple because it is designed to detect. It actually uses YOLO. It's a very popular convolutional neural network for detecting some objects, and it's pre-trained on so many objects already. So you just choose the object you want, and it just chooses it, and it just detects a certain object. In this case, that was apple. So, and I programmed the robot to turn towards apple, and yeah, as you can see, yeah, sometimes. And there's a tricky part about the lighting, because it was probably trained during the day. So if this is a night, you probably need different data set trained and train your convolutional neural network, because it would be like awesome. So this is how it looks from the. As you can see here, I showed you the robot. This robot, the first meeting. I'm not sure if all of you were at the first meeting. Okay, so this is the Jetson part, our computer of the robot who like computes all of the convolutional neural networks. And yeah, this is the camera basically, and this is just how cool it moves. Yeah, just like that. Okay, so attention before visual transformer. It took me 2 days to, like, morning to evening, to learn about some basics of visual transformers, because transformers are really hard to understand. They're much harder than convolutional neural networks. And I'm gonna try my best to explain the best way about visual transformers, but just take to take into account that you might want to look up for that by yourself if you don't understand something. So okay, let's get the ball rolling. I wanted to show the difference between convolutional neural network and visual transformers. And
between vision transformers and the very popular
just some
CNNs.
general things. We will get into details later. It's okay.
And
if you don't
especially
understand. Yeah.
when to use which architecture. CNNs have a strong inductive bias, namely translation invariance. This comes from sliding the learnable kernel over the image. Vision transformers, on the other hand, are like all transformer models, pretty flexible and have no strong bias.
So we have predefined path that CNN works. In visual transformer, it's not actually like that.
Because of the inductive bias, CNNs are also less data hungry, whereas vision transformers need to learn all of the underlying rules of the data. One of the commonly reported statements in the literature is that you should stick to CNNs if you have view data, and use the vision transformer only if you have access to millions of images. Otherwise, CNNs will most likely perform better. CNNs learn in a hierarchical way through a growing receptive field. Vision transformers always have access to all of the components of the image and therefore have a more global way of learning.
Hierarchical means like we have the first input RGB layers and we just convolve through, and the visual transformer, like no, vision transformer, not visual. It's just built different. So what is it? The ViT vision transformer linear layer learns at path embedding. Okay, it's too. I think I made a mistake with the slides here. Wait, let me take a second. Okay, it's too complicated here. Okay, we're gonna return that later. So the first step in visual transformers is to, I'm gonna switch between the slides for the sake of simplicity. Which we just crop our image to the patches. Different size of patches. Regularly is like 16 by 16 patch, and we just align them same way we did here. So we got some array of pictures of patches, and yeah, we also have like RGB layers of those patches, and to work on them we need to project them to some, get like feature extraction of each patch, like of each patch, and just feed that to our transformer encoder. We're gonna speak on that a bit later. So what do we do here? We just take one image, we use some neural network, something that makes our image less, like smaller, and it just extracts the main features. So the dimension of array fits our desired transformer encoder input. For example, what I mean here, transformer encoder will want like predefined arrays from our image. For example, it can be like 668. It's regularly that number of the input layer. So so it can work with that. So you cannot get something larger or smaller. So you need to also to always get some certain number of pixels that is of values, like pixels values that are the same, to fit to our transformer. What I mean by that is, for example, when we get our 16 by 16 patch, and we have 3 layers, R, red, green, blue, we multiply them by 3, so we get 768. But we also might have something like 8 by 3. That would be 16 times 3. That would be 64 times 3. That would be 196, for example. I guess that's right. So, but for example, our transformer takes this amount of number. So this number. So here, this is the input to our transformer. We need to transform this patch to the array that fits this thing that our transformer like kind of takes from our patches. So we need to fit them. How we fit them? We fit them with some neural networks that change our patch to some desired value. Like for example, 767 numbers. We are not getting into details how they work, but yeah, it's somehow predefined neural network. Yeah, behind that. So yeah, and it's just the array from each patch here. Okay, so this is the first step, the basic step we get, and actually this arrays of 768, those are vectors in very high dimension space. For example, like people can only see like 3 dimensions, like x, y, z, but our input has vectors of like, and they have the dimensions of 768. It's maybe hard to understand, but for example here there are some words. This is very abstract thing. I try to understand the best way. Maybe some of you understand it better, probably because you study AI and I don't. But generally, these arrows, these vectors, they describe the meaning of, for example, in this example, those are words. For example, they describe the meaning of the words. In our example, it's just the meaning of the image. So yeah, and yeah, this is just the first layer. And when we fit our arrays to the transformer encoder, we just add one more array. Depending on our goal, for example, if we want to detect the bounding boxes or just the image classification, what is this image, we just add one more vector depending the dimensions depending on the things that we want. For example, if we want to get the bounding box, we get the just like 2 pixels, like describing where is the object, where is the center of the object. So this is just like nothing here. To our interest, it's just zeros at the start. And is that clear? More or less? Okay. I'm really glad that you understand. So, and then those vectors, high dimensional vectors, just enter the transformer. So, and the part bar starts here. So transformers. We take the each of war. Okay. Here I'm speaking of words, but think of every high-dimensional vector, like just the array that describe the vectors, as of token. So, just for example, this is the first token, second token, third token, fourth token, and so on. So here we take the each token and put them through the layers of transformer to tune each token with respect to the context. So the thing that transformer gives to us, it gives us kind of relation between some between the patches. The patches are just pieces of the image. For example, here is the lake, right? And how it can detect that this is the lake? It just like it has this vector. For example, it doesn't know that this lake ends here or whatever. It just knows here I have a lake, and the other patch has some vector describing that here's also some part of that lake, and transformer just makes them, I don't know, some like high level speaking, communicate with each other, so they can relate. They can say, oh, I have a lake in my high dimensional vector, and you also have a lake, so they change, right? So they kind of change their high dimensional vectors described here. Just think of it like they are like aligning together, right? So which each iteration it understands, oh, the lake is closer, so I need to change my vector direction, so it changes. And according on that, it gets the understanding of the whole image. So it understands the context of the whole image. Just quick explanation.
Let's understand.
Okay, no, let's not understand. I'm gonna really try my best with that. So the thing is, think of this a fluffy blue creature roam. Okay, let's just think of it, of these words as tokens. Okay, our tokens as high dimensional. Okay, let's just, for the, I don't know, probably some of you who studied AI understand everything, but there are people who don't, who didn't study AI at university, so I'm just gonna try to be very simple here. So for example, after one patch, we got the vector, which has some values like 1, 2, 3, or whatever, and its size is like 1 by 668. It's depending on the largeness of our transformer. It could be 1,000. It can be whatever, and think of it as token. So the words here are just tokens. So for example, in our transformer we have those kind of matrices. So for each path, for each patch, there is matrix called Q, K, and V. Right? So, and let's switch to the words. Okay, just think of the words like a token, and the token is the same as like our patch. So we need to learn how do we learn how words relate in the sentence. That's like how do we know that before apple we should say the apple, I don't know, like on the tree or whatever. We do this thing, how transform understand. So we generate our for each page we generate new matrix called Q, just large matrix describing it's the page features, and it's in the context of a word. It's kind of asks like, what can be the next one? What can be the next word? For example, for creature, we ask, we made some matrix with kind of like very high level speaking questions, like what can be the next words, and we write them down as some matrix with some values, 1, 2, 3, whatever. I really don't know what is inside and how it works, so so it's just general understanding how it is built. So let's take a look at this example. And key matrix also for every page. For example, there is second page, second token, so to speak, 1 by 768, which has the also like Q matrix, but it also has key matrix. Like for example, this page also has some key matrix, but let's not think of it. So this key matrix, it has kind of answers to our questions. For example, like the Q matrix asks, what can be the next word? And our key matrix responds, like for example, verdant, the, roam, creature, blue, fluffy, a, as in this example. So when we multiply them, as showed here, two matrices on the axis here, we can see that kind of answers. Like, for example, for creature, what can be? Okay, it's probably not about. It's the word that was per. Okay, they were before it, because for example we have really high value here. For example, like blue creature. It's kind of makes sense, right? But blue there doesn't make sense. So it's like small weight. It's small number, small value. Okay, I said you what comes after the word, but let's think of it as before the word, because I kind of confused something here. So, and we learn this way which words can be next, can be before some other words, or next, like depending on our implementation of this problem. So for example here, like creature, like blue, what can be blue? Not roam, not there, not verdant, not forest. Maybe like blue forest, but like, who knows? But it actually got kind of higher value. So the highest value is here, like blue, but let's not talk on that. Let's concentrate on blue creature. It makes sense, right? So after those matrix multiplication, we get this big matrix, which describes how words can relate to other words and how they can be kind of. It can learn the position of the words after some other words. Yeah. So for example, verdant, forest. Yeah, makes sense. And okay, so I'm pretty sure you. Did you get any kind of like something?
Yes.
Yeah, really. I'm really glad to be honest because I thought it would be worth. So this is like same thing that I spoke of, but from the YouTuber that probably knows more.
Let's understand vision transformers. We first divide the image into subimages known as patches. This image patch is nothing but the pixel values of that area of the image. You can see pixel values of single patch. However, since this is an RGB image, instead of a single 2D array, we have 3 channels for each patch. The problem with these patches is that the pixel values range from 0 to 255. We simply normalize these values, and now the input image is ready to be fed.
Wait, normalizing is using softmax function. Yeah, sorry.
Let's understand a total of 64 patches for clear visualization. However, in the actual vision transformer paper, their patch size is 16 times 16. To convert it into a one-dimensional array, we need to flatten all 3 normalized channels of the patch and obtain a vector. We do this for all the patches in the image and obtain a linear vector for each patch. Let's rearrange these vectors for better visualization. Instead of using these normalized pixel values directly after flattening them, we transform them into embedding vectors for each patch. This process involves taking each input and passing it through a neural network to obtain an embedding vector, one by one, for each patch. Now, these embedding vectors can be treated as word embeddings. For the attention mechanism, we take the embedding vector. We make 3 copies of it to feed into the query, key, and value matrices. We get the output query, key, and value vectors for the attention layer. This is a simple process. Here, each embedding vector can be processed in parallel. However, this parallelism creates a problem. I mean, how will the attention mechanism know which patch it is processing?
Oh,
The
yeah,
first patch? Or the 10th patch? Or the last patch? Just like in sentences, where the position of a word is important to understand the meaning, changing the position can alter the meaning of the sentence, even with the same words. The position of each patch is also important to understand the whole image.
I didn't mention
But how do
that,
we
like,
feed
yeah,
position information to the attention part of the transformer? For this, we add positional encoding to the embedding vector to incorporate position information into the vector. After adding position encoding, we get the final vector to feed into the attention block. Now the data seems ready for the attention block to develop relationships between patches. We apply multiple attention blocks and then obtain the output. After these attention layers, final output is ready. At the end, we apply a neural network with softmax for classification. One way is to take the last patch embedding and feed it to the classification network, just like we do in text for next token generation. But actually, we add an extra learnable embedding vector. The goal of this extra embedding vector is to gather all the important information from other patches using the attention mechanism for classification. Then, at the end, we feed this vector to the classification layer to get the softmax distribution for the class label. Now, what is the purpose of the attention block here? If we take the first patch of the image, we calculate the attention of the first patch with all other patches. This way, we can find out how the first patch relates to other patches in the image. The same is the case with other patches. This helps the model understand how different parts of the image are related to each other, enabling it to develop an overall understanding of the information in the image. Now, if we take the first and last patch of the image, we know that the attention between the first and last patch is calculated in the attention layer, and also for all the other patches. So, we can say that this attention mechanism in vision transformers gives it a global receptive field. In convolutional neural networks, we have local receptive fields, so they have a built-in inductive bias. In this image, you can see the texture of the cat because texture is a local feature. Convolutional neural networks may predict the class of the image using the texture of the object. As explained earlier, vision transformers with a global receptive field focus more on global features, like the shape of the object, when classifying it. Remember, these images are not extracted from an actual vision transformer or CNN. I just used them to illustrate the difference between CNNs and vision transformers. This was the image we started with. We have a fixed patch size of 16 by 16 because increasing it to a higher value would prevent vision transformers from gaining a good understanding of the patch. So, the image size should be 128 by 128 for 64 patches. There will be a total of 4,096 attention values calculated at each layer. If the image size is now 256 cross 256, you can see attention increased by huge margin. Now size increased to 512. For an image size of 2048, you can see that the total number of attentions calculated by each layer increases, making this approach less suitable for high-resolution images. But what do you think is an alternative to this vision transformer? Vision transformers cannot compete with convolutional neural networks when there is a small amount of data. Vision transformers require large datasets to perform well and compete with convolutional neural networks.
So, okay. So, what did we? It's been 1 hour and 20 minutes. And what did we learn from this lecture, that the difference between convolutional neural networks and the visual transformers, like convolutional neural networks are straightforward, they need less data, and we're gonna speak on the vision transformers in the future, so you will understand like what do we use it for. It's actually very useful, the transformer build. So for example, if we have an regular image, visual transformer can make us the depth estimation of the image. For example, we don't need depth camera to do that. We can use visual transformers to, for example, if we have one picture, visual transformer can, for example, depth anything. It's called depth anything. Maybe some of you heard of it. Maybe not. I don't know. From an image, it can detect, for example, how far is this object, how far is that object, how far is that object. For example, if we take a picture of in general, it's of course estimated. It's not very precise, but it's very useful in robotics. It's very useful to, for example, if you don't have a depth camera, which like it's always better to use the physical camera than some neural network thing, but well, we can have different circumstances when we cannot afford, for example, a camera so we need to use depth camera, so we need to use the some neural network that will just predict more or less, but also they are really computation hungry. Like vision transformers are harder to compute, harder to process, and yeah. Do you understand the difference? More or less?
Yes.
I'm really glad to hear that. Okay. New thing came out lately. Chinese came out with, as they say, human-like robot. So I didn't watch this video. I added this video before the lecture, so I'm not sure what is shown here. I just wanted to show what happened last week. For this week, maybe you remember that I showed you the different robots the last time. You probably do. So this is a new one. So let's take a look what they got.
Let's be honest, by now we've all seen enough realistic robots online to roll our eyes a little, right? Every few months there's a new headline. This robot walks like a human, or this robot can dance. But then, Xpeng showed up, and suddenly, the line between human and machine got really blurry. Let's be honest, human and machine got really blurry. When Xpeng first rolled out its humanoid robot, called Iron, the internet absolutely lost it. Not because it was clunky or creepy like most prototypes, but because it looked too perfect. Its balance, its stride, even the way it tilted its head, people swore there had to be a person inside. I mean, come on, China unveiling a robot that moves like a living person? The comments went wild. Fake. There's an actor in there. This is CGI. For weeks that was the narrative, but Xpeng wasn't laughing. Behind the scenes, their engineers had spent years creating this thing. Every tendon, actuator, and artificial muscle, only to be told their work was a hoax. So instead of replying online, they decided to show the truth in the most dramatic way possible. At the next press event, they brought Iron back on stage. The crowd was silent, cameras everywhere. The robot walked out, smooth, balanced, with that same human grace that started the controversy. And then, right there under the spotlights, one of the engineers unzipped the synthetic suit. What they revealed was pure metal and circuitry. No actor, no costume, no trickery. Just a mechanical skeleton so advanced it could almost breathe. And then something incredible happened. The presenter actually apologized to the robot. He said, "I'm sorry we had to do this, but we had to prove you're real." You could feel the emotion in the room, because this wasn't just about a robot, it was about trust, identity, and the disbelief that something this good could come from a company from Guangzhou, muscle layers, joint actuators, and precision-engineered servo systems. It was a moment that turned shock into silence, and silence into respect. Now here's where it gets even more fascinating. This wasn't just a PR stunt. Xpeng actually used that moment to launch Iron's next generation, a version so advanced it doesn't just move like a human, it's built like one. This new model has 22 degrees of freedom in its hands, each finger capable of delicate natural motion, a biomimetic spine and muscle system that lets it bend, twist, and balance like a real body, and a curved 3D display head that can show facial expressions and interact with humans in real. We're not ready for about that.
As we spoke before, it's probably teleoperated. There's nothing autonomous in it, but I guess how they trained it, and we are gonna also speak about it. Like they used simulation and reinforcement learning, probably some ESAC scene that my friends work on, and yeah, we're also gonna cover that. So yeah, that's just new thing that came out. Like yeah, better reinforcement learning, more actuators, and more money and stuff. No autonomous robots yet. No AGI, unfortunately. Do you know what is AGI? Like, okay, yeah, not everyone is sure. So, would you like to?
Artificial general intelligence. So basically, intelligence like humans.
Yeah.
Or smarter even.
Yeah, that's correct. So, for example, there's the thing that every company, robotics company, wants to achieve is AGI. Like they want to make them robot as humans, but they unfortunately can't. Or fortunately, I'm not sure. So next time we're gonna, it's gonna be the last lecture on computer vision. We're gonna be done with that. So we're gonna speak about vision, language, action models, and vision language models. Yeah, they're pretty much the same, but similar, but they used in robotics, in the industrial robotics. And yeah, I'm not gonna speak on that too much. So we're gonna learn that next week. And what is the plan looks this way. After we are done with computer vision, we're probably gonna switch to some simulation tools, and I'm gonna maybe show you some, I don't know, interface, and based on that simulation we can also after that we can do some reinforcement learning, and we're gonna try to train a robot. I really want to show that. We're gonna learn how to get the robot from real world to the simulation with the same actuators, with the same variables like torque, I don't know, like speed of moving, so it gets trained in our simulation. I'm not gonna get too far here. So yeah, that was it. Do you have any questions here? Okay, since no questions, we have like 1, 2, 3, 4, 5, 6, 7 people, 8. One guy told me that he's not gonna be here, so like 9, same way as the last time. So I'm really glad to see you guys here. I'm really glad to see you coming here, being interested in robotics and AI. yeah, thank you for coming. That's it.
Thank you.